Well, hello everybody. It is Mr. Keller. I provide a video for the two worksheets. It's actually just one file, but it's two worksheets. If you look closer, let's do this Friday. Make a video and kind of talk about how to do a couple of the problems, get the ins and outs, and then I'll post the answers and you guys can check them as you go. I'm just going to be a completion grade for that. So I will be looking at it and you will have the answers, which is good. We're going to go over the first worksheet is basically given an equation. How do you do a graph? The second worksheet is given a graph. How do you write the equation? Okay. Now, given the equation and writing a graph for at-home learning, you can go right to Desmos or a graphing calculator and type that in and you'll get the graph. However, we're going to live in the world of Gretsch, half graph, half sketch. Okay. So I'm going to go to here. We're going to talk about one of these problems. Hopefully we can all see. This is the worksheet that we're starting with. It's a little bit hard to see on this because it's so blurry, but we can zoom. So the idea that we're going to take down, not this exact problem, but the deal is, I'm hoping this will focus a little bit better. How do I get the graph of number 2 so easily? Why does it look like that, et cetera, et cetera? So I'm not going to do number 2 for you. I'm just making my answer key as I go. We're going to switch to the back of this sheet, and I'm going to go through number 4. So I have it started. I'm going to get rid of this sheet now that you know what we're talking about, though. You can have this as another tab when you watch the video. Here is number 4. All right. So I get myself an axis as such. And for number 4, the actual problem here was f of x equals, f of x equals -3. So that is our reflection. The negative sign is the reflection over the x-axis. The 3 is the vertical stretch factor, as we've talked about numerous times. I have the quantity x plus 3. And then here's the key piece. I have the quantity x plus 1 squared. All right, so if I'm going to graph that, we can put that into a graphing calculator, and it'll do it for us. We'll put it into Desmos, it'll do it for us. However, I'm interested in what can we use, and how can I just literally count boxes and figure this out with some ease. All right, so let's say we take the painstaking steps, which we're not, and we're going to distribute these terms together. So I'm going to first square x plus 1, the quantity, and get x squared plus 2x plus 1. And then I'm going to take that and I'm going to multiply it through x plus 3. So basically, if you think about this in terms of degree, just this guy right here is a quadratic. This guy is a linear. What happens when you multiply x squared by x? Christine. Very good. You get a cubic. Okay? Now, we know that this cubic, the general shape of a cubic from our power functions chart from 100 years ago, it seems, but a couple weeks ago, a cubic looks like that. How does the negative sign, what does that do? Well, the negative sign will just take this thing and give you a graph that looks like this. Now, what will the 3 do? Well, the 3 might take the red graph that was negated and make it look something like that. Okay, and the fact that it has different roots. We have a root here. So basically what I'm going to talk about today is what does that square do? What does that have as an effect? We're going to really kind of hammer out 2 problems, and I think that should be enough because I picked a harder of the graphing problems to do. Okay, but we're expecting a shape that looks something like this. It resembles a cubic long term. Again, if you didn't understand where Christine gave the answer of cubic, it was a quadratic times an x, that's x cubed. So that's a general feel. You should always have your power functions chart out when doing this, because that is the lifeline to power functions and polynomial functions, because polynomials are literally just the sum or difference of power functions. So what do we do? Well, I'm going to look for roots and y-intercepts. There are no asymptotes with polynomial functions because there is no division and there's no square rooting or anything along those lines. So we have no chance to take the square root of a negative. We have no chance to divide by 0. So no asymptotes for this particular graph. It's going to resemble a cubic, which we all know and love from previous years in math. So here's the gist. I know my root. What x values will make this thing equal to 0? Well, it's already in factored form. So I have a root at -3. I also have a root at -1. Of course, they're super close together. Now, I know this is a cubic. So some of you might just take this bad boy and start drawing it and connecting the dots. And then you realize, oh, shoot, it looks like a quadratic. So that's not right. Okay, well, let's think. The general shape that we should have, based on our power functions chart, is a cubic reflected across the x-axis. Okay, so I'm looking for that shape. So what does that mean? Well, as x goes to infinity, then this graph is really behaving like -3x cubed. As x gets wicked big, what happens when you cube wicked big? It gets even wicked bigger. And then you multiply by -3, it means it goes to negative infinity. All right? So as x goes to positive infinity, f of x will go to negative infinity. And that should be pretty easy to follow just by the shape of the graph. As x goes to negative infinity, f of x, so we go left, f of x will behave like negative in big, so like -10 million cubed is -10 billion cubed, times -3. So it's a positive, gigantic number. And again, that should be pretty crystal clear with the graph. As we move left, the graph keeps on going up and up and up and up. So basically how I'm going to do these is I'm going to put in I'm going to find my y-intercept first. I found the roots, I plotted them, I'm going to find my y-intercept, and then I'm hoping that you don't really need to write out all of the as x goes to pieces, because hopefully you have your power functions chart and you're kind of picking up what I'm putting down. But this is the mathematical scenario, what's going on and why that shape occurs. And then I have squiggly equal signs because f of x is basically long-term behaving like -3x cubed. Now, what does it look like short-term? That's why we plotted the roots. That's why we're going to plot the y-intercept as well. How do you find a y-intercept? Easy. You plug 0 in. So if I do this, I'm going to plug 0 in and I'm going to get -3 times 0 plus 3. And then I'm going to get 0 plus 1, which is 1 squared. So if I plug that in, I'm going to do a little quick math. I get -9. So -1, -2, -3, -4, -5, -6, -7, -8, -9. I'll extend my graph a little bit. Okay. Okay. So I have 3 points that I have to hit, and I have to resemble this shape. Okay, well, this is easy. Here's the part of the graph that I need. And then this is going to be easy. Okay, so that part is done. Zoom out a little bit. Okay, you can see the whole picture. There we go. Almost. Okay, so again, as we're going to come down, we're going to hit this point, and then I know that when we hit this point, I have to zoom off to negative infinity, but I got to cross the y-axis. Okay, now the interesting part. What happens at -3? Well, if I'm slightly before -3, the graph is positive. If I'm slightly past -3, I'm not going to do the actual math here, but it is pretty easy to figure out. If I'm slightly past -3, that's like -2.999. Well, if I add 3 to -2.999, this is a positive. This is a positive because we're squaring something. And then I'm going to take a positive times -3. So I know the answer is negative. So I have a sign change. Now, what does the graph have to do here? Well, the graph has to hit this point. The only way you can do that is to turn. And then what really I'm interested in is what's going on at -1. I affectionately call this, and since we're missing basketball season, the crossover dribble or the bounce. All right, it reminds me of a ball bouncing. Now we're upside down on this one, but it's like basically, I don't know, there's a weird app that kids play with too. Some game, like they're just moving like a Pong sort of idea. And you move and the graph's coming from here, it bounces off the x-axis. Why the bounce for the square? Well, a quadratic looks like this. A quadratic upside down or reflected across the x-axis looks like that. We have this scenario right here around -1. That value is being squared. So if I'm slightly before -1, let's say -1.5, I've got -1.5 plus 3, which is a positive. I've got negative 1.5 plus 1, which is negative, but squared makes it a positive. So a positive times negative 3 is a negative value. If I go slightly past negative 1, let's say negative 1/2, I have negative 1/2 plus 3, that's positive. Negative 1/2 plus 1 is positive. Squared is still positive. Times negative 3 is still negative. So there's a bounce. Okay? So when they're squared, the graph has to resemble a parabola there. So overall, that's what your graph looks like for number 4. Okay? All right, I'm switching gears. We're going to give you a graph, and you're going to write the equation. So the graph I'm going to do is problem number 8 on this sheet. It's on the second set, the second number 8. Second number 8. It's given the graph, an ordered pair of negative 1, 6, and we're going to figure out what this polynomial looks like. Okay. This one I don't need the graph for. Wish I could. But you guys will have that in front of you. I'll draw a quick sketch of it. We got a scenario going like this. So that is our graph. Here's our axis. This is, let's call it g of x this time. And then we're going to put in some ordered pairs. So we've got our roots, and we've got some other random ordered pair. Negative 1, 6. Root at 0, root at 3, and root at 5. Okay? And then a root at 0. So if I'm looking at this, this is my picture. We have to come up with an equation for g of x. All right? It's pretty easy. G of x is going to equal a, which is out of the notes, out of the front part of the sheet. That is our vertical stretch factor. All right? It's also going to tell us by the general, just looking at the shape of the graph and looking at that power function sheet, which all of you should have out in front of you, it'll tell you that you're dealing with some sort of parabola-like thing. Okay? So we're going to deal with something that is x squared, x to the 4th, x to the 6th, x to the 8th. X to an even positive power is what we're talking about. Can't be squared in this particular case because we have 1, 2, and I'm going to count this as a double root because there's that bounce again. So what I'm going to do is I'm going to plug in my roots. Now you'll never see me in class. I would never write x minus 0 because we all know that's just x, but I want to make sure that we're understanding root form. This is just like factoring from way back in the day when you guys first learned it. This is the shell of the polynomial. We just have to figure out the a, and then we have to figure out, will this actually be something to an even positive power? So the first thing I'm going to do is I'm going to look to see if I'm right. I'd have x times another x times another x. So this right here is a cubic. A cubic, remember from your chart, looks like that. This graph looks nothing like that. So this is wrong as is. What would I have to do to fix it? Well, it all goes back to that bounce that we just talked about last problem. We have x equals 0 is definitely a root, but there is no sign change. Right before 0, the graph is positive. Right after 0, the graph is still positive. Okay? Now, some people might argue, why can't this be a 4, why a 6, why an 8? Mr. Keller, why are you choosing a 2? Choosing a 2 to make it the least degree polynomial that'll fit this mold. Okay? So, here's the deal. I've got all my roots taken care of. I know the y-intercept because it was given to us. It's 0, 0. So those are all taken care of. There are no asymptotes. And then now we got to think long-term behavior. We have a touchdown-like mentality. As x gets really big or really negative, your graph looks like a parabola. I don't know. My hands look really weird. I'm sorry. So how do I solve for a? Well, I know a is going to be a positive number because of the overall shape. And again, short term, we have some dips, we have some turns, so local mins, local maxes. Long term, the idea is it's basically a parabola. Okay? So what do I do? Well, I've exhausted the x equals 0, the x equals 3, and the x equals 5. those are taken care of in my equation that I set up. We just talked about the 2. We got the bounce. We have no sign change, so it's got to be an even power right here for that particular root. If there was a bounce right here, I would just square the x minus 3 term. Okay? So I have an ordered pair. That's the only thing I haven't used. So what do I do with an ordered pair? You plug it in. All right, now we're going to do a little bit of arithmetic. I got negative 1 minus 0 is negative 1. Squared is positive 1. I've got negative 4. And I've got negative 6. So if I figure this out, we'll do a little quick math here. Negative times a negative is a positive. 6 divided by 6 is 1. So I'm basically solving this brain buster. 1 is equal to 4a. So a is a fourth. And then now you actually have your equation for g of x. It's 1/4 x squared, quantity x minus 3, and quantity x minus 5. And that is how you do those problems. Give you a little hint, because I know there's one on there. It's problem number, it's the second number 5, so it's the one on the very back. The second worksheet, I know it's one doc. One of the roots looks like a cubic here. So what do you assume is going on? Well, when you write it, you would put a 3 with the root that looked like a cubic. Kind of cool. Okay, rewatch the video a couple times if you need it. I'm signing off. Enjoy your day. Alexa, play Slayer.
Here's a station based on Slayer.
Alexa, turn it up. Alexa, stop.